In part 4 of the masterclass, we'll talk about designing and installing for efficiency on the hardware side. And the next part we'll talk about the software. When it comes to the hardware, there are lots of things we can do. We can locate the condenser correctly. We can use water-resistant cooling for the condensers. We can use low TD condensers, and I'll explain what that is shortly. We can use electronic expansion valves. LEDs are a really good idea. And we can make sure the solenoid valve is in the right position. We can ensure that insulation is well done. We can manage air infiltration into our rooms. And we can recover heat and offset gas use or electric heating elsewhere. So let's get into it. Condensers, as I'll take you back to that little diagram I showed you right at the beginning. Condensers need air to cool. They need lots of air. If they don't have air, the temperature will go up and the refrigeration system will use more power. So condensing units need good cooling air. Do not fit them into basements or enclosed spaces. I always pause when I say that because it's kind of obvious that you shouldn't be doing this. And yet it is one of the most commonly done things that shouldn't be. Just yesterday I went on a site and bang, they were up in seating spaces again. So it's very common. And poor airflow will cause the high condensing temperatures or cause the air to be recirculated. And that gives you high power consumption and potentially even a failure of the compressor. So what am I talking about? If you look at that picture on the right, that is a poor little condensing unit in an enclosed space. It's like this concrete alcove or bricked alcove. And I looked at that unit a bit closer. We'll get to that. Here is an example of two groups of condensing units. On the left, you can see there between the seating panels and the plumbing pipework in the seating space, back in the background there, you will see two condensing units. And you see the two condensing units on the right-hand side, which are mounted on the roof. Which do you think will be running more efficiently? Now, I know you can't answer back, but of course the ones on the right-hand side would be running better. So, and why? And I'll show you a good example. This is what you should not be doing. So, left top, that is actually a little cool room for I think it was a little fishmonger. And that condensing unit in the middle was located on top of the cool room behind that sliding door, which was put in place because it was a noisy unit. So when I went to inspect it and I opened the sliding door, it was like 50 degrees air coming out there. And of course the reason why I went there is because the system wasn't working well, was it? But the picture on the right was actually an apartment building in Melbourne, apartment building with shops in the bottom. Is a really good example of what an architect can do to refrigeration, because these units were not allowed to be outside. So you had all the air conditioning units on the left and all the refrigeration units on the right in the car park basement. And that space in the middle is where a car is actually parked. So what you have there is all the air trying to cool the condensing units is being blown at the car and recirculated within that space. So these units will have a very hard time to operate, especially in summer, and that whoever parks his car there will have a very hot car. So that's how not to do that. But just to show the impact that this has on energy use, I've done a few measurements using my trusty infrared gun again. So what I've measured there on this picture, you can see someone was helping me on the left, holding a air on temperature sensor. So that's the air within that space. So this was a small condensing unit in a big market hall. So plenty of air. And you can see the air on temperature was 19 degrees. Okay, not too warm. And then I measured the point where the liquid comes out of the condenser. So that's kind of the condensing temperature, you could call it that. And I measured that with my little gun. And you can see that was 26 degrees. So the difference between air temperature and condensing temperature was about 7 degrees. That's really good. Okay, the system was running well. 7 degrees is a good TD, temperature difference, as I will explain later. And then on another day, I went to this unit where the air coming through the brick wall was 22 degrees, as shown on the left picture. But by the time the air got to the condenser, it was now already at 30 degrees. And the liquid coming out of the condenser was 43. So what we had here was all the way from 22 to 43, we had 21 degrees delta T. So as opposed to 7, the previous one, this one was at 21. So if you compare the two, 14 degrees higher. Remember the rule I said, 2 to 3% per degree, sorry. That would give you something like 30 to 45% excess energy use for this unit as it was running there. Simply because of the location of the unit wasn't well ventilated and it was rather dirty as well. And that was that unit that I showed you initially. So simply because of where it was located, that system was being permanently penalized and using 20 to 30% more power. Another example. Here we have two somewhat larger condensing units. The one on the left was mounted next to the cool room wall, and the one on the right was mounted facing outwards. You can see the trees in the background. Again, the question to you, which one runs better? Well, you don't need to be a genius to work out that the one on the right-hand side is going to work a lot better because it gets the free air from the outside. One on the left was about the width of my hand away from the wall. So you can imagine the difficulty that the air had getting around the condenser and the likelihood of that air then recirculating. There is a rule out there which says at least half a meter away from a wall, or at least half the width of the condenser away from a wall. And very often these rules are not met. Maybe the owner was saying, no, I need the space, back it up against the wall, I don't need it that far away. But again, you're paying a permanent penalty in terms of energy consumption if you do that. So give your units enough air. So the roof mounted is great, shaded is great, don't let them look into the west afternoon sun. Well ventilated, no recirculation, and that will save you energy and also peak demand. On those hot days, that's when you want to get the energy down because that's the network costs that you pay as well. So good airflow saves you throughout the year, and it saves you especially on those hot days. Well, that's the one thing I keep carrying on. Here's an example which I collected whilst I was doing the masterclasses. This is a brand new install, and there we go. This was a large room with a cool room inside, and they installed the condensing unit on top of the room, and the room was completely enclosed. So not only was the condensing unit inside the hot space, but so was the cool room itself. So the cool room was sitting there with 40 degrees air around it, trying to keep itself cool. So not a very good situation. So I see that all the time, even on brand new installs. And it's often not the refrigeration technician's fault. It's often that refrigeration is an afterthought. They think of everything except the refrigeration. This was in fact a brand new, very notable building. And they just forgot to plan for a location for the condensing unit, so they just stick it inside when nobody sees it. Here is one way to solve the problem, where you have a unit ducted to the outside. That can work. You need to allow for the pressure drop in the duct, but if it's properly designed, you can have the unit inside the basement so it doesn't annoy anybody, but you can, even in this case, it actually serves as ventilation for the car park area as well. So water assisted cooling, remember that demonstration I did earlier. Air cooling is the most common way of doing condensing in commercial refrigeration. Water assisted saves energy quickly, and you can get 30 to 40% power at peak, power savings at peak. How do we do that? The cooling tower is the obvious solution, and sometimes this works. I often see large buildings where there is a cooling tower already for the air conditioning, and then they put an air-cooled condensing unit in. It's kind of sad because you could have just tapped into the cooling water and had 30-40% energy reduction. So sometimes one just has to look at what's available. If there already is water cooling available, use it. Don't put air cooling in. And that same building I referred to earlier, they had exactly that water-cooled systems, and bang, they put the air-cooled systems next to the water-cooled system. Makes no sense. Often on a hotel, for example, the refrigeration is like 1% of 10% of the cooling capacity of the hotel. Most of it is air conditioning, and it would make no difference to add it in. I'm not suggesting that you put water-cooled condensers on your butcher shop. That is not a viable idea because it pays money to your water treatment, inspection costs for water cooling. Don't do it only for that reason, but if it's already there, the tip is use it if it's already there. Adiabatic cooling is a really good idea. By pre-cooling the air, you're taking that edge off and you're having the energy gain. It can be a mist spray or a wet pad, but the important point is not to wet the coil. You do not want to get that water onto the fin coil, which is a sensitive aluminium and copper device. The reason is that the copper, the aluminium fins are attacked by the chlorine. That is what I'm going to say. So if you spray water onto the condensers, at best it is a short-term fix. This photograph shows what happens if you install a typical garden irrigation system onto your condenser coil. It erodes the aluminium very quickly, and the reason for that is that all tap water is chlorinated. Chlorine and aluminium kind of love each other, and you see the same thing if aluminium devices are used near the coast. It's the chlorine and the salt that attacks the aluminium. That same effect will happen here. So you need to fully atomize the water so that it doesn't actually wet the surface. Or you could potentially use distilled water or deionized water or the like. So I have seen installations where they use pure rainwater and it kind of works, but the safest approach is not to wet the surface at all. Okay, because if you do, you're going to reduce the heat transfer capability of the coil, and you're also going to reduce the airflow, and that'll give you a higher energy cost. Now there's one solution which is quite clever as a retrofittable solution. I'm always trying to find solutions that work for people with an existing system, and this works well on both air conditioning and refrigeration. So the principle they have is effectively, as you can see on the photograph, is these mesh panels, a little bit like shade cloth, which are stretched in front of the condenser. And on the right hand photograph you can see the sprays which spray against the airflow and periodically just wet the mesh. So you're really driving the air across a wet mesh, and that works really well and is a solution that can be fitted onto an existing system. There are quite a few other similar competing technologies out there, so there are quite inexpensive solutions available to put adiabatic cooling onto your existing refrigeration or air conditioning system. Now, if you have the choice when you're buying your system to select low temperature difference condensers, you should absolutely do so. The condensing unit has its condenser built in. A refrigeration rack, like I showed earlier, has a remote condenser. Advantage of that is that you can pick the remote condenser to suit your rack. What we're talking about here is the KTD. That is the terminology used, three-letter terminology used by our industry, which is Kelvin temperature difference, and that's how you design the condenser. So remember that one picture I showed you of the 19 degrees air coming in and 26 going out? That condenser was running at 7 KTD. So that's good. But the design standard is 14 KTD for no particular reason. That's what the industry is kind of stabilized on. What does 14 KTD mean? It means that on a 30 degrees ambient day, your condensing temperature would be 44 degrees. If you were to spend more money up front on your condensers and go for a larger condenser with a lower TD, let's say 5K or 5 to 10K TD, then you'll actually save 25 to 35% power most of the time. And that's what the supermarkets do. The large retailers, they have in their specifications no more than 7K TD for very good reason. So they're quite happy to invest that additional amount of money because the payback is obviously there. A 7K TD condenser is exactly twice the size of a 14K TD and therefore exactly twice the price. But it's always a good solution. If you are stuck with a 14K TD condenser, there's not much you can do because you don't want to go and replace the condenser. You could then look at the adiabatic option. Just a word of caution, many of the condensing units that are brought into this country today are really cheap, to the point of paying little and, locking in a high energy use. Some of those units are designed with even higher TD than 14K. Some of the units are designed for about a 20K TD, and because they're designed for European or North Asian conditions. They're not designed for Australian conditions. So if you bring one of those units into this country, which many importers do, you have a system that as soon as it's 30 degrees or above, these systems will run at 50 or even 60 degrees condensing and not last long and use a lot of power. We have no energy standards in commercial refrigeration. Air conditioning has star ratings. Most other devices have minimum energy performance standards. These do not exist in commercial refrigeration. Important point to make. So there's nothing which compels an importer of equipment to bring in a generously sized condenser. In fact, commercial incentives encourage him to bring units in with a small condenser because they're cheaper and easier to sell. So that is one thing that I recommend people to ask the contractor is, what is the KTD of the unit that you're trying to sell me? So I can take a considered decision whether I want to take your offer or not. Electronic expansion valves are a nice innovation from several years ago. Up until now, we've been using thermostatic expansion valves, which are mechanical devices, and they have their limitations, as every mechanical device has. A thermostatic or electronic expansion valve wets the coil better, from the inside with refrigerant, and it can also run at a lower pressure of refrigerant. Remember, the pressure that the liquid condenses at, that is the pressure that pushes the liquid through the expansion valve. If you go back to that first diagram, if the pressure goes lower, you're trying to do that to save energy, you get less refrigerant through the valve because you've got less pressure. Electronic expansion valve avoids that. So with electronic expansion valves, especially on larger systems like supermarkets, you can float the head pressure down during cool weather and not lose cooling capacity on your cases. So it's a good thing. It's not really useful for small systems like your butcher shop, but it's really useful for medium to large systems and should be a basic part of, or should be an essential part of an energy efficient system. It doesn't really pay to swap over from a thermostatic to electronic expansion valve. So when you put the system in the first time, put electronic expansion valves in. LED lights. Why am I talking about that in a refrigeration context? Well, the reason is LED lights love cold. So all other lights, fluorescent lights especially, when they're colder, they emit less light. So fluorescent lights in a freezer room, for example, you have to put twice as many lights in to get the same luminescence. They still consume the same amount of power. And then they take a long while to warm up. So if you have fluorescent lights in your freezer room, you have to run them all the time, otherwise they never brighten up. Whereas LEDs, they become brighter the colder it gets, and they use less power. And remember, all the energy that the lights are consuming stays inside the cool room, and it is converted into heat, and your refrigeration system has to suck it back out again. So if you can avoid having lights on all the time, not doing much in terms of generating light, and you can replace those with much more efficient light, which actually becomes brighter when it's cold, and you can turn them off whenever you don't need them, it's kind of obvious that you're going to save energy. So you're not only saving energy with the lights, you're actually saving energy on the refrigeration system because you're putting less heat into the room. And they last longer. So how often don't I walk into a cool room and there are badly running fluorescent lights in the cool room because it's hard to get at and you've got to get on a scissor lift to turn it off, to change them around. With LEDs, you don't have to change them that often. They last much longer. So you get better light, safer maintenance, lower energy use. That's why I think every cool room deserves LED lights. So yeah, there we go. Solenoid valves on condensing units. This is an interesting thing. Now, the expansion valve and the condenser, referring back to my original diagram, in order to control the amount of cooling, because if you just let that system run, it'll just get colder and colder. So to control the amount of cooling and stop it from cooling when it's cold enough in your room, you turn the liquid supply to the expansion valve off. And that's done with a solenoid valve. And the way most systems work is it's cold enough, the thermostat turns the solenoid valve off, then the evaporator runs out of refrigerant, the compressor pressure goes down because it's now sucking a lot of nothing, and then the control turns it off on low pressure. And it sits there until the room temperature comes up, solenoid valve opens, liquid goes back in, pressure goes on, and the compressor turns back on. And that cycle repeats itself again and again and again. And that's entirely okay. Now, what happens when the solenoid valve shuts? As soon as it shuts, between it and the expansion valve, all that liquid still keeps flowing. All that liquid empties out through the evaporator. So if you have your solenoid valve far away from your evaporator, all that liquid still has to empty out. And your compressor has to run that excess amount of time. And what actually also happens is that liquid line itself becomes cold. So if you have your solenoid valve far away from your cool room, you're actually cooling the environment and you're running a compressor much longer than you should. And that is very inefficient. So that solenoid valve on the picture on the left, I think it actually goes into a bigger picture. If you see that one there, there's the little red box around the solenoid valve. Condensing units like these are supplied with solenoid valves because very often the condensing unit is placed right on top of the cool room, and then it's okay to have the solenoid valve there. But if that condensing unit is 20 meters away, that solenoid valve needs to be relocated, and very often it is not. Here is an example of an installed unit located on the ground. In this case, I know that the cool room is 20 meters away, and yet the solenoid valve is on there. And what you can typically see is condensate forming on your liquid line. And yes, the client is basically paying for cooling the environment in addition to the additional runtime. Here is an example of what it should be. There you see the bottom of an evaporator in a cool room, and the solenoid valve is installed inside the cool room immediately ahead of the expansion valve in the cool room. That's correct, and it will operate much better. Now, in actual fact, this is something that every refrigeration technician is taught. And sometimes they install the solenoid far away because it saves them a few meters of electric cabling. And sometimes there's no particular reason, maybe just being forgetful. But it often is something that needs to be reminded, and one needs to point it out. So when you do the first install, make sure you get it right. It's not easy to justify closing down the whole system, pumping it all down to relocate the solenoid valve. The energy saving you get from that is small, and you can't prove that it's going to ever pay back. But doing it right from the outset is a good strategy there. Here's an example, again on my tour through Victoria, where I found this solenoid valve, which you can see there at the bottom of that picture, located outside the room, again about 15 to 20 meters away from the evaporator, right next to the condensing unit on the right-hand side. So it's common, it's very common, and it's not correct. Then insulation. The most common insulation we have is this black closed foam insulation, soft, spongy stuff, which you can see in the right bottom picture. It's very effective, it's good insulation, it's resistant to moisture when it's new, and it's inexpensive. So that's why it's widely used. Unfortunately, it's easily damaged by traffic because it's soft. You know, if you kick it, if any hard object gets to it, you can easily rip it. And it's not very durable in ultraviolet light. So, and of course, because it's black, it absorbs heat. So if you put that out in the sun, you're trying to insulate something and you've got a black surface and it'll suck up the heat, so that's not very smart. So you need to clad it. In high traffic areas and in outside areas, that insulation does need to be clad. So not like on the left there, where you have these long runs up on the roof in the sun with absolutely no protection over them. So protected from the weather and the sun. If you don't do that, this is what happens. So on the left-hand side, you can see the insulation having shrunk away from the support point. On the right-hand side, you can see the insulation badly degraded by ultraviolet light. And eventually the moisture penetrates and it loses its insulation capability. Here is examples again of black insulation on a roof, or even many sites that don't have insulation at all. That's, again, a historic relic, but back in the 60s and 70s, one just didn't bother insulating, and that's a bad thing. So here is an example of aftermarket or insulation solutions that you can buy from this insulation provider. Clip-on insulation can be quite expensive. An alternative is to do something like this, which shows you colour bond sheeting designed to fit over the insulation so that it is protected when it's up on the roof. So there are ways, and the contractor can think of these ways to protect that. If it's well protected, it'll last the life of the plant, and it's an investment that you as an owner will make, so make sure that you protect it. Infiltration. Air entering a cool room or a freezer room is one of the biggest sources of heat load. So you want to get as little air as possible coming in. And the moister the air, the more energy it contains. So up in Darwin, the air is what we call nearly saturated. And in an environment like that, the moisture in the air actually contains more energy than the air itself. So just removing the moisture is the biggest source of heat load on the room. In Melbourne, it'll be less, but still the moisture is the thing that you want to avoid, because A, it's a heat load, and B, what happens to it? It becomes ice on your evaporator. So we need to install barriers to prevent air from entering. And here you can see examples of what we call plastic strip curtains. Plastic strip curtains are a necessary evil because they don't last, they have safety issues, they become opaque, and the accidents have happened with people being hit by forklift trucks coming through a strip curtain. But where it's only walk-in access, a strip curtain is relatively safe. But you'll see the picture on the right-hand side is strip curtains applied to a abattoir where carcasses are pulled past the strip curtains. And that's a serious hygiene issue because they come in contact with the strip curtains, and theoretically you're supposed to wash them after every carcass, but who really does? And the left side shows a strip curtain that is just simply too short. It's 0.5 meter off the bottom, and that is completely useless. You might as well not have that. So strip curtains are a good idea, but they require maintenance and they need to be replaced, and they cost a bit of money. But it's a good option to, if you have to leave the door open for extended periods of time, at least have a strip curtain on your doors. With bigger doors, more commercial environment, insulation or technology that has improved a lot over the years is self-opening doors or sliding doors, quick acting doors, which can be either the vertical type or the horizontal type. They are now so good that some models can even be pushed out by the forklift truck, and then they roll up and they come back into their tracks. And they are produced with a range of insulation, and some of them are even trace heated. So quick acting doors, which open only for a short time, automated, are an entirely viable technology. And whilst they're expensive, it's cheaper to have one quick acting door than replace your other door 5 times because the forklift truck has run it out of the frame. So quick acting doors is a good energy saving solution. Heat recovery. Every refrigeration system, as we know, rejects heat to the environment. That's what the condenser is there for. And depending on the refrigerant, this temperature can be quite high. Now, some of that heat can be recovered because the minute it leaves the compressor, the gas is quite hot. It's called what we call superheated. And that extra heat, which could be, some gases could be 80, 90 degrees when they come out of the compressor, can be recovered in the way of hot water. So we have, in the simple case, as shown on this diagram, we have a hot water tank, and the the discharge gas that comes from the compressor is simply routed through this tank before it goes to the condenser, and it just lifts that water up to typically 50 to 60 degrees. So that's a classic solution that has been used by supermarkets forever, really. So most supermarkets have all their hot water coming from the refrigeration system. And that avoids electric or gas heating. Thank you. Sustainability Victoria supports action on climate change and reducing energy costs. If you would like to find out more, please visit the Sustainability Victoria website.